Good morning, everyone. My name is Supraja, Assistant Professor in the Department of Civil Engineering, B.V. Raju Institute of Technology, Narsapur. Today, I am going to teach three-moment equations and its applications. So, what is three-moment equation? Where we can use this three-moment equations? So that is my first criteria, three-moment equation. So this is applicable for indeterminate structures, especially for continuous beams. Now we'll see the derivation of three-moment equation. So let us consider a continuous beam ABC. So this is a two-span beam from a continuous beam. So let us assume the length of AB span is L1, length of BC span is L2. Now let us assume moment of inertia of AB span as I1 and moment of inertia of BC span as I2. Now let us consider a horizontal line passing through the B and the deflection of A with respect to B as HA and the deflection of support C with respect to support B as HC. Now let us consider E as Young's modulus. Now let us draw an elastic curve of support B like this. Now let us assume this point as A1 and this point as A2. This point as C1 and this point as C2. Now this deflection is HC. Now from the diagram, so we have drawn on tangent through the B. Now this is the rotation theta at B in AB span and theta in BC span. Now for the equilibrium condition of joint B, this rotation should be same in opposite direction. Now from this diagram we can write tan theta is equal to, so this one, that is A1 A2 by, so opposite side by adjacent side, that is L1, that is AB span, is equal to, for BC span we can write C1 C2 by length of span BC, that is adjacent side. So this is opposite side by adjacent side. Now we want A1 A2 and C1 C2. Now we can find out A1 A2, this one A1 A2. So we can write A1 A2 in terms of A1 and A2 and HA. This whole deflection is HA. So now we can write HA, that is AA2 minus AA1 will give A1 A2. Now A2 will be HA from the assumption minus A1 A2. So A1 A2 is deflection of A from tangent of B. This A1 A2 deflection of support A with respect to B. Now we can find out this by using M by EI diagram. Now let us consider the beam like this. Now draw the M by EI diagram for this. So M by EI diagram we will get from the free bending moment diagram case. So in this case, let us assume each span is a simply supported beam with given loading conditions. Now from that we'll get, say for example, AB span is subjected to an UDL of W kilonewton per meter and BC span is also subjected to W kilonewton per meter intensity. Now, so we'll get for UDL case, we'll get BMD as second degree parabola. Now, we want this maximum ordinate that we'll get. So, we know that for maximum bending moment, when a simply supported beam subjected to UDL is, so WL square by 8. Now, this is WL square by 8. Now, this is also WL square by 8. Now we want A1, A2. A1, A2 is H1, HA minus this HA is, so already we have gone through this. So this is A2. So here for deflection profile, we'll get tangent like this. So this will be A1. Now this will be HA. Now we can write HA A1 A2 as HA minus moment of M by EI diagram between B and A from A. So this is this M by EI diagram of this free bending moment diagram as well as fixed bending moment diagram. So let us assume in this case moment at A as MA, moment at B as MB and moment at C as MC. Now we'll get fixed bending moment diagram will be like this. Now we have to deduct moment of both free bending moment diagram and fixed bending moment diagram areas from the HA, that is a deflection of A with respect to B. Now we can write HA minus of now moment of M by EI diagram. So that is this is the free bending moment diagram and this is a fixed bending moment diagram. Now let us assume A1 as area of free BMD, this one, area of free BMD for span AB, Now let us assume small a1 as CG of free BMD for span AB from left support, that is from A, from support A. Now let us consider A2 as area of free BMD, for span BC. This one, this is A1 and this is A2. Now let us consider small a2 as CG of free BMD for span BC from support C. Now this is A1, this is A2. Now this is A1, small a1 and this is small a2. Now this is support A, support B and this is support C. So we have fixed BMD like this. This is MA, we are assuming. This is MB, so this is MC. So if supports A and C are also fixed supports, we'll get moments at A and C also. Now to find these unknowns, we are finding A1, A2, that is HA minus moment of M by EI diagram. Now this we can write HA minus, let us consider here for fixed BMD, let us consider this is A3, area A3, and this is for BC span, let us consider this is A4, and for AB span, let us consider this triangle as A5 and this is A6. So we are dividing two trapezoidal sections into two triangles and two rectangles in case of ABC span. Now we can find out the moment of each area from boundary conditions. Now coming to the free BMD, we can write M by EI, that is moment of M by EI. Now these two diagrams are called as M by EI diagrams. Now we can write 1 by EI1. So now we are writing this moment of M by EI diagram for AB span. Now we'll get A1, that is moment of area A1, that is this one. So A1 into small a1, that is CG of this area A1 from support A, that is small a1. Now we can write same thing for fixed BMD in span AB. So that is, this is the rectangle. Now for A3, so area of rectangle as, so this is L1 and this is MA. So MA into L1, centroid, CG of this area A3 is, for rectangle it is L by 2, that is L1 by 2 for AB span, that is L1 by 2 plus we have a triangle in AB span, that is in the form of triangle. Now we can write moment of this triangle area, that is area of triangle as half into, so base as L1 into, so we want this portion, that is this total, as we are assuming MB as greater than MA. Now we can write this value, that is MB minus MA. So this value as MB minus MA for span AB. So that we can write MB minus MA. Now this is for AB span. Now this is equal to HA minus 1 by EI1 into A1 small a1 plus MA L1 square by 2 plus, we can write like this one, MB into L1 by 2. Here we have to write a CG of this triangle from support A, that is this one. So this is from apex point, this as 2L1 by 3. So this is 2L1 by 3. This is L1. Now we can write MB into L1 by 2 into 2L1 by 3 minus, we can write MA into L1 by 2 into 2L1 by 3. Now this can be written as HA minus 1 by EI1 into A1 small a1 plus MA into L1 square by 2 plus, so this can be MB into L1 square by 3. Now this can be written as MA into L1 square by 3. Now from this, HA minus 1 by EI1 into A1 plus MA into L1 square by 2 minus L1 square by 3 plus MB into L1 square by 3. Now we can write A1, A2 as HA minus 1 by EI1 into A1 plus MA L1 square by 6 plus MB L1 square by 3. Now A1, A2 can be written as HA minus 1 by EI1 into 6A1. So just to take the LCM of these three. So MA L1 square plus 2MB L1 square by 6. Now we can write A1, A2 as HA by 6, take this 6 outside, so we'll get 6EI1 into 6A1 plus MA L1 square plus 2MB L1 square. So now, let us assume this is equation number 1. Now similarly, we can write C1, C2. So from the diagram, from the support conditions, so this is C, this is B. So this is C1, this is C2. Now we are finding C1, C2. C1, C2 represents deflection of C with respect to B. Now we are finding C1, C2. So C1, C2 can be written as, so this as HC. Now we can write C1, C2 as CC2 minus HC. CC2 minus HC will get C1, C2. This small deflection of C. Okay. So to find this, we are writing some moment of M by EI diagrams. So this is MA, this is MB, and this is MC. So same concept again we are going to apply for BC span. So we can write CC2 as, so this is a deflection of C with respect to B minus HC. Now this deflection will get from moment of M by EI diagram. Moment of M by EI diagram for both free BMD and fixed BMD. So this is called free BMD and this is fixed BMD. Now this is minus HC. Now C1, C2 can be written as moment of free BMD for BC span. So that is this one for BC span. So this is, let us assume A2. This is area A2. Now we want this height for, in case of fixed BMD, that is MB minus MC. And this span as L2. Now we can write moment of M by EI diagram for BC span, that is, so for area A2, so this is A2, that is area of BC span multiplied with CG of A2 area from C, that is small a2. Then we have fixed BMD also here, that is plus, we have 1 by EI2, so flexural rigidity. So this is applicable when the different spans of moment of inertia are different. Now, for fixed BMD, it is MC into L2, and for this triangle, so we have to write area and the CG of this triangle. That is, now for rectangle, this is L by 2, L2 by 2. Now plus for a triangle, it is half into L2 into height, that is MB minus MC into CG of this triangle from C. That is from apex point, it is 2L2 by 3 minus we have HC. Now this can be written as 1 by EI2 into A2 plus MC L2 square by 3 plus MB. So 2 will get cancelled. So MB L2 square by 3 minus this one MC L2 square by 3 minus HC. Now 1 by EI2 into, so we can write this as A2 into small a2. So MB into L2 square by 3 plus, in these two terms, we can take MC L2 square as common term into, this is 2 here, MC L2 square by 2. Now, if you take common MC into L2 square, so we'll get 1 by 2 minus 1 by 3 from this, minus HC. Now, we can write 1 by EI2 into A2 plus MB L2 square by 3. Now, this can be written as, so we can take LCM as 6. Now, 3MC L square into 3 minus 2 minus HC. Now, so C1, C2 can be written as 1 by EI2 into, so if you take 6 as LCM, we'll get like this, 6A2 plus MB L2 square by L2 square. So we'll get 2 MB L2 square plus MC L2 square minus HC. Now C1, C2 can be written as 1 by 6EI2 into 6A2 plus 2MB L2 square plus MC L2 square minus HC. Now let us assume this is equation number 2. Now already we know that tan theta is equal to, so A1 A2 by L1 from the diagram. So this is C1 C2 by L2. Now we can substitute, let us assume this is equation number 3. After substituting one and two equations, in equation 3, that is tan theta is equal to A1 A2 by L1 is equal to C1 C2 by L2. Now we'll get MA into L1 by I1 plus 2MB into L1 by I1 plus L2 by I2 plus MC into L2 by I2 is equal to minus 6A1 by I1 L1 minus 6A2 by I2 L2 plus 6E HA by L1 plus 6E HC by L2. Now this is called three moment equation when the span is having different moment of inertias and there is a sinking of support case. So for example, if there is no sinking of supports, then these two will becomes 0. And also we can write, so when the spans of having same moment of inertia, we can write MA L1 plus 2MB into L1 plus L2 plus MC into L2 is equal to minus 6A1 by L1 minus 6A2 by L2. So this is called three moment equation or Clapeyron's theorem of three moments. This is called Clapeyron's theorem of three moments. Now we can apply this three moment equations into indeterminate structures. So this theorem is applicable only for three moment equations. So this theorem is applicable only for indeterminate structures, for continuous beams, and these are not applicable for trusses and frames. Now we'll see the application of Clapeyron's theorem of three moments for two span continuous beam. So let us assume this is the two span continuous beam and these are the support conditions. This is A, and let us consider support B. This is support B and this is support C. So let us consider AB of span 4 meters and BC of span 6 meters. Now AB is subjected to an UDL of 20 kilonewton per meter and BC span subjected to a concentrated point load of 30 kilonewtons from C. Now this is 2 meters. Okay. Now moment of inertia of AB as I and moment of inertia of BC as 2I. Now we know that three moment equation for two span continuous beam, that is MA into L1 by I1 plus 2MB into L1 by I1 plus L2 by I2 plus MC into L2 by I2 is equal to minus 6A1 by I1 L1 minus 6A2 into A2 by I2 L2. Now here there is no sinking of support, so we are neglecting the deflections here, deflection case. Now we want here area of free BMD and fixed BMDs. Now for this case, let us draw the free BMD. Let us draw the free BMD for both AB and BC span. Here AB span is subjected to UDL of intensity 20 kilonewton per meter. So we'll get BMD diagram as parabola and the maximum ordinate as for AB span as WL square by 8. This is from simply supported beam. So this is equal to, so intensity of UDL and length of AB span as 4 meters. Now we'll get 40 kilonewton meter and BC span subjected to concentrated point load. So in this case we'll get BMD diagram as a triangular in shape. So this is of magnitude, that is maximum ordinate for BC span as is equal to, so this is eccentric point load. In this case, maximum ordinate as WAB by L. So a simply supported beam subjected to eccentric point load. In this case, maximum BMD is maximum bending moment value as WAB by L. Now here W as 30 and A means this one, B2, support B2, concentrated point load distance, that is 6 minus 2, 4 meters, into B as 2 meters divided by span of BC as 6 meters. So from this we'll get maximum ordinate in BC span as 40 kilonewton meter. So this is 40 kilonewton meter and this is also 40 kilonewton meter. Now we can find out area A1, that is, this is area A1 and this is area A2, and also we want a CG of area A1 from support A and CG of area A2 from support C. So this is a small A2. Now A1 is, this is a parabola, second degree parabola. So we know that area of parabola as 2 by 3 AB. So this is equal to 2 by 3 into A means a span of AB here, span of AB, that is 4 meters, into B means maximum ordinate of parabola, that is 40. Now from this we'll get area A1 as 106.67 and we want a small A1, that is CG of area A1. So area A1 is equal to 106.67. Now we want CG, that is a small A1 is, so for parabola this is a symmetrical parabola. So in this case center CG is located at midpoint of parabola, that is L1 by 2, that is span of AB by 2, that is 4 by 2 is equal to 2 meters. This is meter square. Now we want area A2. So to calculate this area, so for BC span, so this is a triangle. So we want area of this triangle, that is half into, so base is here, span of BC, that is 6 meters, into maximum height of this triangle as 40. Now from this we can write A2 as 120 meters square. Now we want a small A2, that is CG of area A2 from support C, that is, this is eccentric triangle. So in case of eccentric triangle, CG is located from left side, it is L plus A by 3, and from right side it is L plus B by 3. This is a CG formula, center of gravity formula for a eccentric triangle. So this will be, now here we want from C we want, so this distance we want, this will be L plus B by 3. So L plus B by 3. Now this can be written as, so small A2 can be written as L plus B by 3. So that is, so span of BC as 6 meters and B as 2 meters divided by 3. So from this we'll get 8 by 3 meters. Now we can apply 3 moment equation here, that is MA into L1 by I1 plus 2MB into L1 by I1 plus L2 by I2 plus MC into L2 by I2 is equal to minus 6A1 small a1 by I1 L1 minus 6A2 small a2 by I2 into L2. Here we know the value of A1 and small a1 and capital A2 and A2. Here we know the value of L1, that is a span of AB, that is 4 meters, and L2 as a span of BC, that is 6 meters. And also in question given that moment of inertia of AB span, that is AB span, that is I1 is equal to I. I1 is equal to I for AB span. Now, moment of inertia of BC, that is we are assuming as I2. So, that is 2 times of BC span. Now, after substituting all these values, we can find out support moments at each support. Here, in case of given condition, supports A and C are hinge and roller supports respectively. So here there is no moment in case of MA will be 0 at support A, and MC will be 0 at support C, because support A is a hinge support and support C is roller support. So these two will not take the moments. So at these two cases conditions, final moment will be 0. But support B is a roller one. It is an indeterminate support. It is intermediate support. So for intermediate support, that is middle support, will exhibit moment. So definitely, one moment in AB span and one moment in BC span. So these two moments at joint B will be same in magnitude and opposite in direction. Then only this entire structure will be in stable condition. So this satisfies the equilibrium condition. So now we know that MA equal to 0 and MC equal to 0. Say for example, if support A and support C are fixed supports, this 3-moment equation is not applicable for fixed ends. So in that case, we have to convert fixed support into determinate support. So either hinge or roller. So in that case, we can find out support moments in different way. So here in this case, A and C are hinge and roller supports. Now, so MA will be 0 and MC will be 0. Now this term and this term becomes 0. Now we can write 2MB into L1 as 4 meters and I1 as I for AB span plus L2 as 6 meters and I2 as 2I is equal to minus 6 into A1, capital A1 as 106.67 into small a1 as a CG of area A1, that is 2 meters, divided by here I1 as I into L1 as 4 meters minus 6 into area A2, capital area A2 as 120 into small a2 as 8 by 3 divided by I is 2I for BC span and span as L2 as 6 meters. So after this we'll get 2MB into, so this will be 2I, 8 plus 6 is equal to, this entire term will be minus 320.01 by I minus this entire term will be 160 by I. So from this we'll get MB value, that is minus 34.29 kilonewton meter. So this is the support moment at B. So at support B we'll get 2 moments. One is in BA span and one is in BC span. So now we want support reactions. So to find the support reactions, we have to consider support moments also. So here at support A, we'll get a reaction RA, and at support B, for BA span, we'll get one reaction at B, and for BC span also, we'll get another reaction at B. So let us assume for AB span it has RB1, for BC span it has RB2. Now at support C we will get C. Now MA and MC both will be 0 and from MB is, so one should be clockwise and another should be anti-clockwise at support B. Then only this joint will be in stable condition. So this value is 34.29. This is 34.29. Now AB span subjected to UDL of intensity 20 kilonewton per meter and BC span subjected to eccentric point load of 30 kilonewtons from C. Okay, this is 4 meters. This is 4 meters. Now take the to find the support reactions RA, RB and RC. So take the moments about A for AB span, then we'll get reaction at A and reaction at B for span AB. Now after that, take the moments about C, or we can take moments about B also. Now for AB span, take the moments about A. So that is sigma MA will be 0. Now, so how many reactions we have in AB span? One is RB1 and moment at B we have and applied load UDL. So now due to RB at A will get anti-clockwise moment like this. So we are taking clockwise as positive, anti-clockwise as negative. So due to RB will get RB1, that is minus RB1 into perpendicular distance between RB1 and support A, that is 4 meters, and we have clockwise moment at B, that is plus 34.29. This is already a moment, a clockwise moment, so that's why we are taking it as a positive, and we have UDL on AB span. So convert this UDL into point load while determining support reactions. So this will, after converting this point load, this UDL as point load, it will act at midpoint of UDL and it generates a clockwise moment at A. So that is plus 20 into 4 into perpendicular distance between point load of UDL and support A as 4 by 2, midpoint 4 by 2 is equal to 0. Now from this we'll get RB1, that is 48.57 kilonewtons. Now from equilibrium condition of vertical forces, that is sigma sum of all the vertical forces equal to 0. So we can write RA and RB1 are acting upwards. So these two are positive and applied force as negative. So we can write RA plus RB1. So upward forces are positive, downward forces are negative. So is equal to, so UDL load as, convert this UDL load into point load. So that is 20 into length of UDL. So from this we can find out RA, that is RA is equal to 31.43 kilonewtons. This is for AB span. Now let us consider a BC span by taking moments about C, that is sigma MC will be 0. Now in BC span we have RB2 reaction at B and there is an anti-clockwise moment at B and we have an eccentric point load on BC span. So due to these three we'll get moment at C. Now first find out the moment due to RB2 about C. So this RB2 will generate a clockwise moment like this about C. Now that is clockwise moment as positive. So RB2 into perpendicular distance as 6 meters. Next we have anti-clockwise moment at B, that is anti-clockwise moment as minus. So minus 34.29 and we have concentrated point load here. So it will produce an anti-clockwise moment about C, that is minus 30 into perpendicular distance between 30 kilonewtons and C as 2 meters. So this is equal to 0. So from this we'll get RB2 as 15.715 kilonewtons. Now by applying sum of all the vertical forces equal to 0 for BC span, here RB2 and RC are upward forces and 30 kilonewtons as a downward force. So RB2 plus RC is equal to 30 kilonewtons. From this we'll get RC as 14.285 kilonewtons. Now we want a total reaction at B, summation of RB1 and RB2 in AB span and BC span. So we want total RB, that will be total RB as RB1 plus RB2. So RB1 as 48.57 plus RB2 as 14.285. So we'll get total reaction at B, that is 64.285 kilonewtons. So now we want shear force diagram and bending moment diagram. So this is support A, this is support B. So while drawing shear force and bending moment diagrams, we have to draw the projection lines from the supports. So this is 30 kilonewtons. Now draw the projection lines from A, B, C supports and also from the loads. Now to draw the SFD, let us take the reference line. Now we know the RA. So RA is 31, that is positive. So RA is a positive value, that is above the reference line. So this is 31.43 kilonewtons. So this is 31.43. Now in between AB we have UDL. So convert this UDL into a point load. So this UDL intensity as 20 kilonewton per meter and the span as AB span as 6 meters. So 20 into 6 will get 120. So 31.43 minus 120. So we'll get 119 point some value here. This is 119. So next RB is acting upwards. We got RB as 64.285. So this 119 as negative. So minus 119 plus RB is 64.285. So we'll get plus 15.715. So this is above the reference line again. Now in between B and concentrated point load, we don't have any loads. So SFD will be constant. Shear force will be constant. Now here this is plus 15.715. We have a concentrated point load towards down, that is minus 30. So we'll get 14.285. So from load to C we don't have any loads between. So this is again 14.285. Finally this here, this shear force value and shear force value at C will be same. So then only this SFD values are correct. So now this is above the reference line as positive, below the reference line as negative. So this is positive, this is negative. So this is positive, this is negative. So this is SFD. Now we want BMD for this. So to draw BMD, again draw the projection lines from all the supports. This is A, this is B and C. So this is 30 kilonewtons, this is 20 kilonewton per meter. So draw the projection lines like this. So just by combining free BMD and fixed BMD, we'll get the final BMD. So we know the value of MA, that is moment at A, as 0 and moment at C also 0. So this is the 0 0 line, reference line, and we know the value of MB, that is MB as 34.29. Just to join these values, we'll get fixed BMD for the given case. Next, in AB span, due to applied loads, we know the free BMD, that is parabola, second degree parabola, and this ordinate as 40. In case of BC span, we'll get triangle due to point load. So this value is also 40. Now enter this zone will be neutral. This zone will be neutral. And this zone in BC span will be neutral. Now above the fixed BMD is positive and below the fixed BMD as a negative. So this is positive. Now this is negative. So this is called BMD. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.